Hello everyone, my name is Zhang Liang from Inner Mongolia University. Today I am pleased to present our work, titled SGFR Track, Uncertainty, Gated Spectral Feature, Restoration for Online Multi-Object Tracking. This work focuses on online, multi-object tracking or online MOL in many existing trackers. The main effort is usually placed on improving the association strategy. However, in challenging scenes, the appearance features themselves may already be corrupted by occlusion, verpose changes or nearby identities. If the input feature is unreliable, the matching module can only make decisions based on degraded evidence. Therefore in this paper, we take a different perspective. Instead of only improving the matching rule, we aim to repair degraded appearance. Features before association. The core idea of SGFR track is simple. Better association starts with better evidence. This presentation is organized into 4 parts. First I will introduce the motivation and explain why feature degradation is a critical problem in online multi-object tracking. Second, I will present a key observation. Occlusion-induced feature corruption can be interpreted as high-frequency temporal noise. Third, I will introduce the proposed SGFR track framework, including the gating funnel and the spectral guided feature restoration module. Finally, I will show the experimental results, ablation studies, qualitative examples, and efficiency analysis. Online multi-object tracking aims to locate multiple targets and maintain their identities over time. Most modern trackers follow the tracking by detection paradigm. They first detect objects in each frame, and then associate these detections with existing tracklets. However, in real-world videos, especially in crowded or highly dynamic scenes, targets often occlude each other. They may also have abrupt motion, large pose changes, and similar appearances. Under these conditions, the extracted appearance embeddings can become unstable. For example, when a person is partially occluded by another person, the feature extracted from the image crop may contain mixed information from both identities. This makes the temporal feature trajectory unstable and less discriminative. As a result, the tracker may confuse nearby targets, causing identity switches and fragmented trajectories. Existing methods usually try to solve this problem from the backend association side, such as improving motion prediction, matching rules, or global context modeling. These methods are useful, but they usually treat appearance features as fixed inputs. Our motivation is that if the feature itself has already been degraded, downstream association can only compensate for imperfect evidence. Therefore, we propose to restore the feature before it is used for matching. The key observation behind our method comes from a signal processing perspective. For the same identity, the appearance feature should evolve relatively smoothly within a short temporal window, although there may be pause changes or viewpoint changes. The identity-consistent information should not fluctuate sharply from frame to frame. In contrast, occlusion-induced corruption often appears as sudden temporal jitter when the target is partially occluded, blurred, or mixed with nearby identities. The feature sequence may contain unstable high-frequency variations. To analyze this phenomenon, we apply the discrete cosine transform, or DCT, along the temporal dimension of feature sequences. We observe that clean samples tend to concentrate more energy in low-frequency components, while occluded samples show stronger energy in high-frequency regions. This suggests that stable identity information is relatively smooth, while occlusion corruption behaves more like high-frequency temporal noise. Based on this observation, we formulate feature repair as a selective spectral denoising problem. The goal is to suppress harmful high-frequency perturbations while preserving identity-consistent information. Based on this idea, we propose SGFR track. The overall framework contains 2 main components. The first component is the gating funnel. It decides whether a tracklet really needs feature restoration. This is important because not all high-frequency variations are harmful. Some variations may come from real rapid motion or useful appearance changes. If we restore every tracklet blindly, reliable features may be oversmoothed. The second component is the spectral guided feature restoration module, or SGFR. For ambiguous tracklets, SGFR transforms the temporal feature buffer into the frequency domain, suppresses high-frequency corruption using an adaptive spectral filter, and then transforms the feature back into the time domain. In this framework, clear tracklets bypass the restoration branch, while ambiguous tracklets are selectively repaired before Hungarian matching. This design makes the method both effective and efficient. Now let us look at the gating funnel. The key idea is to use association uncertainty as the control signal. Specifically, we propose the bidirectional matching margin, or BMM. First, we compute the forward margin for each tracklet. We compare the similarity score if it's best match detection with that of its second best detection. If this margin is large, the tracklet has a clear preference. If this margin is small, the tracklet is uncertain between multiple detections. However, only considering the forward direction is not enough. The detection may be the best candidate for one tracklet, but it may also be strongly competed by other tracklets. Therefore, we also compute the backward margin, which measures whether the selected detection is uniquely owned by this tracklet. Only when both the forward and backward margins are sufficiently large can the association be considered reliable. If the minimum bidirectional margin is small, the association is ambiguous, and the restoration branch is activated. This design brings 2 advantages. First, it saves computation, because clear tracklets bypass SGFR. Second, it prevents over-smoothing reliable features. In other words, the gating funnel makes restoration selective rather than universal. For ambiguous tracklets, we apply the spectral guided feature restoration module. This module has 3 main steps. The first step is mirror extension. Since the feature buffer is short, directly applying a spectral transform may introduce boundary artifacts. Mirror extension improves boundary continuity and makes the frequency representation more stable. The second step is DCT transformation. We apply DCT along the temporal dimension of the feature sequence. DCT is suitable here because it has good energy, compaction ability, smooth identity. Consistent temporal patterns are usually concentrated in low order coefficients, while unstable occlusion-induced jitter appears more strongly in high frequency coefficients. The third step is adaptive, but are worth filtering. The filter strength is controlled by the uncertainty signal from the gating funnel. When association uncertainty is high, the cutoff frequency becomes lower, and the filter suppresses more high-frequency noise. When uncertainty is moderate, the filter preserves more temporal details. After filtering, we apply inverse DCT and use residual fusion to obtain the restored feature. The residual design keeps the original observation as an anchor, so the restored feature will not deviate too much from the input. SGFR Track is easy to integrate into existing tracking by detection pipelines. In our implementation, we integrated interbot sort under the unified box model framework. The process is straightforward. First, we compute the initial cosine cost matrix between active tracklets and current detections. Second, for each tracklet, we estimate the association uncertainty using the bidirectional matching margin. Third, if the tracklet is ambiguous, we apply SGFR to its historical feature buffer. Fourth, we use the restored feature to update the corresponding row of the appearance cost matrix. Finally, we perform Hungarian matching using the updated cost matrix. This integration is lightweight. We do not retrain the detector. We do not introduce a heavy temporal backbone. The DCT-based restoration has low computational cost, and it is activated only for ambiguous tracklets. Therefore, SGFR Track keeps the original online tracking pipeline almost unchanged while improving the reliability of appearance evidence. Now let us look at the quantitative results. We evaluate SGFR Track on 3 standard benchmarks: dense track Mo 17 and Mo 20. All experiments follow the unified box Mo protocol with YOLO XX detections and LMBN Duke appearance features. On dense track, SGFR Track improves the BOT sort baseline from 60.0 to 61.1 in HOTA, from 92.6 to 92.8 in MOTA, and from 61.5 to 63.0 in IDFE. This result is important because dense track contains frequent interactions, severe occlusions, and highly nonlinear motion. These conditions make association especially difficult, and appearance feature restoration becomes particularly useful. On MOT1, SGFR Track achieves 69.9 HOTA and 78.5 MOTA, showing strong performance in conventional pedestrian tracking seen on iOS. On MOT2, which contains extremely crowded scenes, SGFR Track also achieves the best HOTA and MOTA among the compared trackers. Overall, these results show that SGFR Track consistently improves tracking robustness across different scenes on iOS. More importantly, the results support our main argument. Improving the quality of appearance evidence before matching can lead to better identity association. We further conduct ablation studies to analyze the contribution of each component. First, applying SGFR to all tracklets improves identity-related performance, but it may slightly affect overall stability. This shows that spectral restoration is useful, but it should not be applied indiscriminately. When we add a confidence-based gate, the performance becomes better. However, the best result is achieved by RBM-based gating funnel. This confirms that bidirectional association ambiguity is a more effective signal for deciding when feature restoration is needed. We also analyze the spectral design. Mirror extension improves performance by reducing boundary artifacts in short temporal windows. The Butterworth filter performs better than the Gaussian alternative, suggesting that its frequency response is more suitable for preserving stable identity structure while suppressing high-frequency corruption. The sensitivity analysis shows that the method is relatively stable around the gating threshold of 0 to. If the threshold is too small, some ambiguous cases are not repaired. If the threshold is too large, the method may become too aggressive and process reliable tracklets unnecessarily. The qualitative example further shows that SGFR Track is effective in partial occlusion and crossover cases, where the target is still visible, but its appearance feature is contaminated. Efficiency is also important for online tracking. To isolate the overhead introduced by SGFR, we measure the runtime of the tracking and association stage only, excluding detection and read feature extraction. On dense track, the speed decreases only slightly from 440.0 fps to 420.0 fps. On MOT1, the speed changes from 160.0 fps to 151.0 fps. The small overhead confirms that SGFR Track remains compatible with real-time online tracking. The efficiency mainly comes from two factors. First, DCT-based processing has low complexity. Second, the gating funnel activates restoration only for a subset of ambiguous tracklets. It is also important to clarify the limitation of our method. SGFR Track is most effective for partial occlusion crossover and feature contamination cases. When the target is completely occluded for a long time, the visual signal itself is absent, and spectral restoration cannot recover information that is not observed. In such cases, the method naturally relies on the motion model of the base tracker. Therefore, SGFR Track should be understood as a complementary appearance repair module, rather than a replacement for motion reasoning. To conclude, we propose SGFR Track, an uncertainty-gated spectral feature restoration framework for online multi-object tracking. The main contribution is to address association errors from the perspective of feature restoration before matching. First, we introduce ABM-based gating funnel to estimate association uncertainty and activate restoration only for ambiguous tracklets. Second, we design a spectral guided feature restoration module that uses DCT domain adaptive filtering to suppress occlusion, induce high-frequency noise. Third, experiments on dense track MOT17 and MOT20 showed that SGFR Track consistently improves tracking performance while preserving real-time speed. The final takeaway is simple. Better association starts with better evidence. By repairing degraded appearance, features before matching, SGFR Track provides a lightweight, interpretable, and practical direction for robust online multi-object tracking. Thank you for watching.